That was a great presentation by Mr. Woodmeyer. Thank you for that. Our last presentation will be done by Mr. David Yinks, and he will be speaking on the bomb calorimeter experiment that we conducted.
How's everybody doing tonight? My name is David Yinks. I'll be reporting on an experiment we did last week, the bomb calorimeter. Quickly, I'm going to introduce you guys to the apparatus that we used. It's not nearly as exciting as the name may or may not imply. So here we have a well-insulated, assumed to be adiabatic boundary. We're going to assume that there's no work being done in the system and that there's no heat transfer from within inside to the outside environment. These are all assumptions that have to be made to get any kind of useful data out of this experiment. So, but within the vessel, we have our stainless steel container that combustion will actually take place. The igniter and the ignition source on the outside, the thermocouple leads, and a stirring apparatus to homogenize the heat within the vessel. Okay, so goals of this presentation. We're going to find the thermal capacitance of the calorimeter. This will let us find the heat of combustion of other fuels, unknowns, but in this case, peanuts. We're going to compare to what we've gotten from other sections and give a little bit of an insight on what these numbers compare to the real fuels that we use and encounter every day. So here we have our benzoic acid. We have this as a known heat of combustion value. This is what we can use to calibrate our specific apparatus and get the experimental values within some kind of reasonable accuracy. These are the peanuts that we're going to be burning, combusting. We'll comment on comparability. It's a little difficult to about 28 grams. Okay, well, when I read it earlier, it was not a well-defined 28, or it was not a well-defined weight. I looked at a jar of peanuts in my house to try to, I actually borrowed this picture from a friend of mine. This is of the actual peanut brand that we used in the lab. I looked at some peanuts that I had in my house and I did not have a 28 grams next to it, just in a quarter cup. So a quarter cup would have been difficult to get kind of an accurate weight. This is our ignition wire. The ignition wire is something we also have to account for in the experiment. It does contribute a certain amount of energy when it does combust itself. This is a close-up of the actual apparatus that we're going to be using. It's a small crucible within the vessel that will house the fuel, and it's in contact with the ignition wire to ensure complete combustion. Also, when we pressurized up this vessel, we would add a little bit of water to make sure that we were using the lower heating values, because it would be difficult to calculate where we would lie within the upper and lower limits of combustion. So if we can just keep it at a constant lower heating value for every time we run it, it eliminates one more thing we have to take into account. The purpose of us pressurizing the vessel to 30 atmospheres each time was to completely get rid of all the other elements that we can find in air, as well as ensure that you have an excess of oxygen present in order to have very complete combustion of the fuel within the vessel. This is all sealed up, getting ready to be pressurized, and this is the actual apparatus as it sits ready to collect data. the first run that we did it with benzoic acid. This is our node. This is used to be able to calibrate the vessel, calibrate the apparatus to get the experimental values. The whole experiment is just an application of the first law. And here you can see that we use arranging so we can get our constant for the vessel itself. This constant can be used to calibrate when we combust unknown material. Here's our time versus temperature graph of the peanut, our unknown sample. As you can see, it took about 5 minutes to get to the equilibrium temperature, or excuse me, about 4 minutes. Here's a few of the calculations that we're to run through to get the actual heat back, to get the heat energy per gram. So the delta T, the mass, and subtracting out the energy that was supplied by the wire give us the Q of the peanut. And here we're going to compare this to some of the other groups. I do have to admit that I made a mistake when I was using my Excel charts. So these values are not nearly as accurate as they should have been. Jared had a more accurate standard deviation, which is about 2,000 joules per gram. And according to the internet, an accepted value of peanut combustion is 2,300 joules per gram. So the average still wasn't terribly far off. The average was corrected, but these numbers are not. There was a standard deviation. So just a quick comparison against other common fuels. Benzoic acid and peanuts, relatively low in comparison to fuels that we burn for harnessing power for internal combustion engines or, other such devices. And to wrap it up, this is what we've determined from our particular experiment. Any questions?
What sentence is that picture?
That was just the Hindenburg. Just to give you an example of how much energy there is within hydrogen.
I was just curious because of the tower and stuff.
Yeah. Absolutely massive. Orders of magnitudes different between peanuts and hydrogen. So you can see why we don't put peanuts in cars.
Are we calculating the higher heating value of the fuel or the lower heating value?
The lower heat value, I believe, because we would not be turning anything into, we would not be vaporizing the fuel itself. So it would keep the fuel at the lower heat value. I may have that mixed up. Actually. Yeah, I did. Okay.
Was the combustion of the benzoic acid more like an explosion, whereas the peanuts was like a flame that fizzled out? Because it's kind of funny to think peanuts just, explode.
Yeah, it is kind of like trying to visualize it. It'd be really awesome to have a camera inside that thing. But since we have the excess oxygen, it was, when we did press the igniter switch, there is no sound. It's very anticlimactic. A little light comes on and that's done. So I would assume there's no explosion. It just would completely combust. I don't know how quickly or not, but obviously quickly enough to assume that it would be an adiabatic process for the time here.
So is it done on under pure oxygen?
Yes, so more or less pure oxygen, just to ensure that there's no other variables when you're combusting, and to make sure that there's the excess, because you have your fuel triangle, ignition source, fuel, and oxygen. So if we have excess oxygen and you have your ignition source, the only thing left that's going to be limiting the reaction would be how much fuel you have. In this case, peanut and benzoic acid.
Do you include the stir in the calculation, the work done by the stir?
So
Do you include the work done by the stir in the calculation?
No, we do not. That's something that we have to kind of neglect here. Yes, there is some work being contributed to the system by an electric motor turning some viscous fluid but it's going to be assumed that it's so low that we can neglect it for this experiment. And it's also constant from run to run to run. So the calibration that we did with the benzoic acid sort of takes into account all the other variables acting on the assumptions each time. Thank you guys.